The scientific method. The scientific method is how chemists think. It's also how other scientists think, but we're not talking about other scientists right now. We're talking about chemists because this is chemistry class. So the scientific method is a way of learning, and it emphasizes observation and experimentation. It is very different from philosophy. Philosophy involves sitting around and thinking about stuff. There is a need for philosophers. There's a place for that. But science uses a different method of learning. We observe things and we do experiments. We test our ideas. So the scientific method is not a rigid procedure. It's not, okay, well, I'm going to do step 1 and step 2 and step 3, and then I'm going to come to the answer. Sometimes we wish it were like that, but it's actually much messier than that. The scientific method is an approach to solving problems, but it can look very, very different from person to person. There are 4 key characteristics in the scientific method. Here's sort of an overview. So the starting point would be with observation, and that can lead to a hypothesis. Hypothesis then will be tested by experiment and confirmed or revised, and so sometimes we go around in this loop for, a decade or 2 before we figure things out. Observations can also lead to laws. Laws are also tested and confirmed or revised by experiment. And the hypothesis can lead to theories, which again, we subject everything to testing because we're skeptical. We're not just going to believe that, somebody in London said, well, this is what happens when you do this. We're like, oh, really? I'm going to try it and see if it happens here too. So this is the overview. We'll talk about the specifics. So the first step in the scientific method is generally an observation. An observation or a measurement. There are different types of observations. Some of them you can make with your naked eye. Others require instruments, either measuring devices or perhaps fancy microscopes or something like this. But it usually involves some measurement or description of some aspect of the physical world. You observe something. An example of an observation. This guy is Antoine Lavoisier. He lived from 1743 to 1794. This is not a history class. I'm not going to quiz you on the dates and the names of the scientists, but I'm going to tell them to you just so you can get a feel for how old some of this information is. So, these scientists, when you think about the things that they discovered, given their limited resources, electricity hadn't been discovered yet. How do you do scientific experiments without having any electricity? I mean, these guys worked under very primitive conditions, and yet they made some really amazing discoveries. So anyway, this guy was interested in combustion, burning things. It's kind of a common theme. Most chemists, I think, are secret pyromaniacs. It's fun to burn stuff, right? The thing is, we know how to do it. We learn how to do it so that nobody gets hurt. And that makes it even more fun when you don't get hurt. So anyway, he studied combustion by burning substances in closed containers. And what he observed was that the mass of the container and its contents did not change. So think about a fireplace. Back in the day when we actually were allowed to burn wood in our fireplaces, when you burn a log in the fireplace and the fire is burned through and it's all done, does the log weigh more, the same, or less than it did when you started? It weighs less, right? You just got a pile of ashes. The initial log might have been really heavy. The ashes are light. You blow on them and they blow away, right? So he was studying things in a closed container. I think this is one of his containers that he burned things in. So he would take, obviously, smaller things than a log, and he would burn them, but in a closed container. And he'd weigh the container before and weigh the container after, and the mass didn't change. And so that's an observation. Observations lead to the formation of hypotheses. That's plural. The singular is hypothesis. Hypothesis. IS. A hypothesis is a tentative explanation of the observations. So Lavoisier observed that the mass didn't change. So his hypothesis, his explanation for that was, well, I think it's because when something burns, it's combining with something in the air. And in my closed container, because what's burning is combining with the air, then the mass doesn't change because it's just combining and changing in there, but nothing's going away, nothing's coming in. The hypothesis is why you think the observation occurs. Why is this happening? Some hypotheses are pretty far-fetched and crazy. But what's important is that it be falsifiable, that you could test it and possibly prove it wrong. So he did test this. We take the hypotheses and we test them with an experiment. An experiment is a highly controlled environment. We control everything that we can, and we do the experiment to either disprove or validate the hypothesis. Like, okay, well, if I burn this in the container without any air, then the mass might change. That might be the hypothesis. The experiment. And so you might try that, and then you would find that it actually wouldn't burn without the air. And that might confirm your hypothesis. Well, it didn't burn at all without the air, so this supports my hypothesis. You cannot prove it to be correct, but you can prove things to be incorrect. So what if your experiment shows that your hypothesis is wrong? Well, sometimes you can just modify it. Oh, well, let's just add this little phrase. We'll just tweak it a little bit, and let's test it again. Other times you realize your hypothesis really sucked, and you just have to throw it out and start over again. And that happens too. So if you revise it, you have to test it again. And this is where you get the going around in circles thing. You have the hypothesis, you test it, you revise it, you test it again. You revise it, you test it again. Around and around and around. And some people call this fun. When we have a number of similar observations, that may lead to the development of a scientific law. A scientific law is a brief statement that summarizes what happens, and it can be used to predict future events. So here I have a pen. You've heard of the law of gravity? What does the law of gravity say will happen when I let go of this pen? It's going to fall. It does that every single semester. It's so awesome. Law of gravity always works. Observation that bodies that are not supported by anything will fall towards the center of the earth. Law of gravity. Does it explain why the pen falls? No. In fact, scientists are still working on exactly what is gravity. We're still not super clear on that. It's kind of mysterious. But the law of gravity is an observation, doesn't tell us why, but it tells us what happens, and we can use it to predict the future. We can predict that if I drop this piece of chalk, it's also going to drop. Sure enough. Scientific laws are also subject to experimental testing. So back to our example with Lavoisier, he developed the law of conservation of mass from his observations and experiments on burning things. And the law of conservation of mass states that in a chemical reaction, matter is neither created nor destroyed. This came out of his burning things in closed containers and seeing that the mass of the entire container didn't change. It does not explain why, it just says what happens. The hypothesis can lead to a scientific theory. So we've got a well-established hypothesis that lots of different people have tested, and everybody agrees, yeah, this seems to be how it is. This seems to be the best explanation for what's going on. Then it can become a scientific theory. Theories provide explanations for observations and laws. They are a model of how nature is. They often predict behavior well beyond the initial observations on which they were founded. And again, they are also subject to experimental testing. Scientists like to do experiments, and we like to test anything we can think of. So Lavoisier's law of the law of conservation of mass led to John Dalton's atomic theory. So he lived 1866 to 1844, the next century. But he used Lavoisier's law and took it further and developed a hypothesis that became well established and is known now as the atomic theory. So here's a comparison of these two, because it's important to understand the difference. The law states what happens. It comes from observations. It may prove to be false. The theory tries to explain why. So law is what, theory is why. Theories come from hypotheses. Theories can also prove to be false. But a theory is as close to truth as science can get. We cannot prove anything to be correct. The best we can do is to say, no one has come up with a way to prove this incorrect. And so until we know more, this is what we're going to take as true. So here's a conceptual checkpoint. Most of the book has examples. I think this version calls them skill builders. And I will do a lot of examples in class. In this chapter, there's no math, there's no problems to do, so we'll do this conceptual checkpoint. These are embedded in the chapter, and as you read through the chapter, I would encourage you not to skip over them, but to look at them and make sure that you understand them as you go along. Because if you don't understand what you've just read, going on ahead is not going to be a good use of time. So this is asking us which statement most resembles a scientific theory. Remember, the theory explains why observations happen. So A, when the pressure on a sample of oxygen gas is increased 10%, the volume of the gas decreases by 10%. Does that sound like a theory? No. What does it sound like? An observation. It sounds like an observation. And if enough people observe the same thing, it could become a law. Let's look at B. The volume of a gas is inversely proportional to its pressure. Inversely proportional means that when one goes up, the other goes down. Is that explaining why? Nope. The way this is stated is more general than the first statement, and yet it's kind of saying the same thing. This is also an observation and possibly a law. It says what happens, doesn't say why. A gas is composed of small particles in constant motion. That is a theory. It doesn't really sound like an explanation, does it? Is it something that can be directly observed? Can we see the individual particles in constant motion? Can you see the air molecules? I can't. It's not something that can be directly observed. This is actually an explanation. This is a theory. This is measurable. This is measurable. This can't be measured. This is explaining why, explaining what's going on instead of just stating what is happening. So this is a scientific theory. And then D, a gas sample has a mass of 15.8 grams and a volume of 10.5 liters. That's just a straight out observation. We took this sample, we measured its volume, we measured its mass. We're just saying this is what it is. So any questions about that? Are atoms real? I was just telling you, you can't see atoms. If you use a very, very fancy, very expensive scanning, tunneling electron microscope, we can get images like this. And then, of course, scientists have some, it's no good just taking pictures of random atoms. Let's spell something with the atoms. So these are the kanji characters, the Japanese characters for the word atom, written using individual iron atoms on top of a copper surface. So this is our best visualization of an atom. It makes them look cone-like. They're actually spherical as far as we can tell, but this is at least evidence that, yes, atoms do exist. We can get these crude pictures of them. There's another book I've taught out of, and they spelled out, do your homework in atoms. I don't know how long that would take, but it would be rather involved.